in today's lecture, we'll discuss about the certain things about a dipole, which are what is an electric dipole, what is electric field due to dipole, and what happens when the same dipole is kept in an external field, and about the equilibrium of dipole. Okay, so let's dive in the topic of electric dipole. First of all, what is an electric dipole? So we define a dipole with an arrangement of, dipole is defined as an arrangement of equal and opposite charges kept nearby. So dipole basically is an arrangement in which we have equal and opposite charges and they are just kept near each other. Okay, so we can just imagine a dipole with a charge, we can say a negative and a positive charge, and these two charges are kept at some distance nearby. So we can say let this be minus q, let this be plus q charge. As you see, these are equal and opposite charges and they have to be kept at a distance, let the distance be d. So this technically is called as an electric dipole. So what do we study for this dipole? What are the things we want to know about this dipole? First of all, we quantify this dipole with a quantity which is called as electric dipole moment. So we quantify this quantity with something which is called as electric dipole moment. So electric dipole moment means we are assigning a quantity for this particular dipole, and that quantity will tell us what is the strength of this dipole. Not only that, it will tell us where is the positive charge and where is the negative charge. In other words, it will tell us what is the direction this dipole is having. Okay, so this quantity which we are assigning is called as electric dipole moment, and we denote it with the letter P. And note that it is a P vector, so it has a magnitude as well as a direction also. So let's say what is the magnitude of this P? The magnitude of dipole moment, simply we call it dipole moment, but we know that it is electric dipole moment because you will be having one more time the discussion on this dipole, and that time it will be the magnetic dipole moment, right? So here it is related to the charges, it is the dipole created from the charges, so that's why we here say it is the electric dipole moment. Okay, so let's see what happens here. The magnitude of this electric dipole moment is given as 1 of the charge multiplied by the distance between them. Okay, so what you have to do, you have to take 1 of the charge, either positive or negative, obviously they are equal and opposite, so you take the magnitude of it, whatever the charge is, and multiple the distance between the two charges. So this is the magnitude of dipole moment. So we write down magnitude of dipole moment is q into d. Okay, now after this magnitude we assign the direction also. So what is going to be the direction of this dipole? What is the direction of this dipole moment? So in physics we have a convention that we write down the direction of this dipole moment from negative to the positive charge. Okay, this you have to remember, we assign a direction from negative q to positive q. We assign a direction of this dipole moment from negative charge to the positive charge. But you may have seen or you may have studied in your chemistry also that in the chapter, I guess in chemical bonding, the dipole moment is denoted or it is assigned from positive to negative. In other words, it is denoted from the less electronegative element to the more electronegative element or the more electronegative atom, because that time you need to know where is the more electron density aligned, which one is the more electronegative element, right? So let's take that, for the sake of this confusion, I am telling you, in physics you should know that dipole moment goes from minus q to plus q in physics, right? We are assigning a direction of minus to plus. So this is the direction of the dipole moment and this is the magnitude of this dipole moment. So now this is what we have. The dipole is basically an arrangement of equal and opposite charges, and dipole moment is a quantity we will assign to this. So this P is the quantity we are assigning here. it tells us the magnitude as well as direction, or we can say strength of this dipole. So it is given by one of the charges multiplied by distance, and the direction is from negative to positive. Now just imagine if I ask you, what will be the net charge of this dipole? What is the net charge of this dipole? What is the net charge of this dipole? Since it is equal and opposite, so you may be knowing that when it's equal and opposite, the net charge is 0. Let it be -5 plus 5. Okay, -5 coulombs plus 5 coulombs, the net becomes 0. In other words, whenever you see a diagram or a question in your paper, in your exam, which will be having a net charge 0, so we may think that it may be a question of dipole. Okay, it is just a hint I am telling you, not always, not necessarily always, but maybe sometimes whenever the sum of the charges given from a particular diagram is 0, so we may just think that it may be a question of dipole. But remember, here when we write down the magnitude of that electric dipole moment, we don't write down the total charge, no, we write down the one of the charges. Here you can say, when we use this Q, it is one of charge. Okay, that is the electric dipole moment. Now let's see some more things about the dipole moment. Now first of all, what is the SI unit? Since it's a quantity, it's a vector quantity, what is the SI unit? Okay, so SI unit of dipole is coulomb meter. Why it is so? Because as I said, the magnitude of dipole is charge into distance. So if we see what is the SI unit of the charge, it is coulombs. Remember, it is capital C. And what is the SI unit of this distance? It is meters. So it becomes coulomb meter. So that's it, coulomb meter. And what should be the dimensional formula? So if you see for the dimensional formula, charge is having current into time. So this is the dimensions of charge, and dimensions of length is L1. So we have L1, T1, A1. You can see L to the power 1, T to the power 1, A to the power 1. So this is the dimensional formula, and this is the SI unit. Okay, great. Now let's see what in different cases can be the dipole moment of the particular thing. Here it is the charge is minus Q and plus Q. So what is the dipole moment? If they ask, we will say it is from minus to plus, and how much is that? Again, the dipole moment is given as magnitude Q into L, since the distance is L. So we take one of the charge, multiply by the distance. Now if the same question is asked in this way, that we have this dipole, but the length is not denoted by L, it is now denoted by 2 times of A. Again you will say, so dipole moment is given by Q into 2 times of A. So this is the magnitude of dipole moment. But A, why it is giving 2 times of A? So that we can have an idea that the half of the distance of the charge from the midpoint is A, and the distance of this charge from the plus Q from the midpoint is again A. So we can think like this, that if there is existing some midpoint, the negative lies at a distance A and positive also lies at a distance A. So total length is 2A, right? So sometimes it is the half of the distance. That's why it is 2 here. And before that, when we use this L here, it is the complete distance. That's why it is L here. Okay. Now let's see, when the dipole is a vector, so technically we can say every property of a vector will be applied to the dipoles as well. In other words, the electric dipole will follow every property what a vector is following always. So we'll see what is this. It's asking find dipole moment in the given case. So what is the dipole moment? How do we do it? We say fine, we can just say these are the two separate dipoles. Let's find out dipole moment in each case. So here we will say it is minus to plus. And what is the magnitude of it? Q into 2A. So we can write down, this is say dipole moment 1, it is 2 times of Q into A. And what is the second one? So it's also Q into 2A. And what is the magnitude of it? Again, it is P2 is 2 times Q into A. Now you can see you have been given two vectors here. Two vectors are going in the same direction. Let this be P1 and let this is P2. P1 and P2 are given in the same direction. So how do we calculate their resultant? So net dipole moment, as I said, it is following every property of vector. So when vectors are aligned in the same direction, their magnitude is given by just the sum of their magnitudes. So we can say it is P1 plus P2. And now it will be equal to 2 times of QA plus 2 times of QA. It becomes 4 times of QA. What is the direction of it? when we sum the two vectors aligned in the same direction, their resultant is again in the same direction. So it will be aligned in the same direction. So this is how we deal with the vectors when we deal with the dipole moments when the multiple dipoles are given, right? We can think in this diagram they are made up of like two dipoles here. Now let's see one more problem here based on this. So how do we do it? It is given, first of all, dipole moment in this case. So you can look at the diagram and see it is given that there is one negative 2q minus 2q charge at the origin, and somewhere there is plus q and other place there is again plus q. First of all, is this a dipole or not? There are only 3-point charges, but is this a dipole or not? When we pair up the charges, we have two equal and opposite. So either two charges can make a dipole, 4 can make a dipole, 6 can make a dipole. But is this a dipole or not? Can it make a dipole? Can we think in this that it can be a dipole or not? So yes, it is also a dipole. So how? These are the three charges. Can three charges also make a dipole? Technically yes. Now if I ask you what can be the net charge of every particle here, net charge of all these particles. So you can think like this, minus 2q, okay, minus 2q, then plus q and plus q, it sums up to 0. As I said, if from a particular set of charges you have the net charge becoming 0, that means that is behaving as a dipole, that may behave as a dipole. So let's see if it is behaving as a dipole, what is the net dipole moment and what is the direction of that net dipole moment. So how can we do it? We can imagine that this minus 2q which is at the center, it can be imagined like this one. See, minus 2q at the center, I am imagining it as q and q. I am imagining it as minus q and minus q at the origin. So what is the net charge at this origin? You can see net charge is still minus 2q. It is still unchanged, minus 2q, correct? Now after this we had one positive charge, okay? We have one positive charge at a distance 2a. We have one more positive charge at a distance 2a. Clear? So the dipole lengths are now, dipole lengths is now, this is 2a, this is also 2a, and this is plus q also, and now this is also plus q. So we can just say this is actually combination of two dipoles, minus to plus q, correct? And this minus is contributing as a dipole moment, dipole one of the charge for the dipole for this one, dipole on the x-axis, and this is acting, this one q is acting as a charge for the dipole on this one, and they are aligned at theta degrees from each other. So you can imagine there are two dipoles, this one and this one aligned at angle theta, and you can see if I ask what is the dipole moment of this, you can say sir this is equal to 2qa. And what is the dipole moment of this one? You can also write down 2qa, because one of the charge is q and the dipole length is 2a. It is given in the from the diagram, okay? Now if we have two vectors, let this be p and let this be p, two vectors are at angle theta, so where is their resultant? So their resultant is always at their angle bisector whenever we have the two vectors. If this is theta, so it will be aligned here theta by 2, it is aligned here theta by 2, and this is our dipole net. And how much is the magnitude of this net dipole? You must be knowing the sum of the two vectors when they are inclined at some theta angle. So we used to write it like this, root of first vector square, second vector square, because here first and the second vector are of equal magnitude, that's why I'm writing p square plus 2 times of first vector into second vector into cos of angle between them, and the angle between them is complete theta, okay? So this is how we do it. And now when we proceed, maybe in vectors you had studied that if there are two vectors at an angle theta and both the vectors are equal in magnitude, so when we proceed by this, we will get it as 2 times of p into cos of half of angle theta by 2, okay? 2p cos of half of angle. How does this come? It is just we just proceed with the derivation and we get it, okay? We proceed with this and we get it. So we can say what is the net dipole moment here? So the net dipole moment here is this thing. And what is the angle with which it is inclined? So you should note that it is inclined from the x-axis at an angle of theta by 2. So it is inclined at an x-axis at an angle of at theta by 2 from positive x-axis in anti-clockwise direction. So you have to go from the x-axis in anti-clockwise direction at a half of the theta. If this is 60, you will go at a 30 degree, and there is the dipole moment, and there is the net dipole moment, and the magnitude of which is 2 cos theta by 2. Is that clear? I hope it's clear here. So now let's move to one more arrangement of charges. Let's see this. There also, if this is a dipole or not, let's calculate first of all the total charges here. So the total charge here is, you can say, what can be the net charge here? Minus 3q. What is here? Plus q. What is here? Plus q, and again plus q. So you can see the net charge here is summing up to 0. So if the net charge sums up to 0, as I said, whenever the net charge is summing up to 0, it may be a dipole. So it is actually a dipole, and here also you have to guess what is the dipole moment. So let's find out what the question is saying. Question is saying that every charge is aligned at an distance a from the center of it. So from the center, every charge is aligned at a distance a. So let me make one more arrangement here. So here you can see it is minus 3q. So this minus 3q, now I will split in 3 equal charges. Fine. So this minus 3q, I will split in 3 equal charges, and every charge I will be writing as minus q, and minus q, so that every negative charge of this minus q will act as a one of the charge for the 3 dipoles. So this minus 3q will make a dipole with this plus q, one of them, and you can see rest of the charges are a and q and q and q. This is plus q, this is plus q, this is plus q. Done. Now here I will say there can be the dipole. First of all, there is a dipole from this minus to plus q. There is one more dipole from on the opposite side, just symmetric to it, minus to plus. Can you guess what is the dipole moment of this one? One of the charge is q, and what is the length between this and this? Looking at the geometry of it, can you see this distance is a and this distance is a? So what is this hypotenuse you can see? So if I say there in this diagram, if you copy it in this diagram, this is a and this is a. How much is this hypotenuse? So it can be a under root of 2. So this distance is a under root of 2 between the charges. Okay. So now here we see what is the distance. It is a under root of 2. So this is the dipole moment here. The same will be going this side, q into a into under root of 2. So there are 2 dipole moments, and one more dipole moment. Wait, one more is, you can say one more, minus q into plus q. And what is the length of this dipole? So it is a plus a. It is double of a. So we can write down q into 2 times of a. So there are actually sum of the 3 vectors you have to perform. Sum of 3 vectors, qa root 2, qa root 2, and q into 2a. Now remember, this qa root 2 and this qa root 2, these two which are denoted by here green color, okay, these two, if you see these two are actually at what angle, so that we can find out the sum of the two. They are at 90 degrees. So why are they 90 degrees? Look at the geometry of it. Can I say this was a triangle which is actually isosceles, and this angle will be equal to 45. Isosceles equilateral triangle, so other than the 90 it has to be 45. So this is 45 on one side, 45 on the other side. So how much is the total? 90. And if we have 2 vectors equal in magnitude aligned at 90, so what is the sum of these two? So we can write down sum of these two is given as one of the vector multiplied by root 2. So it is root 2 times one of the vector. And how much was one of the vector? Q into a into root 2. So I will say in spite of this and this, okay, these 2 vectors which are right and left like this, I am using one vector which is having a magnitude of root 2 times qa root 2, and now how much it becomes? It will be equal to 2 times of qa. But wait, it is not our answer. It is not the net dipole moment. Why? Because it is just the sum of the 2 green color vectors. In other words, you have just found out what is the sum of these 2 vectors, green color. But still there is also one yellow color dipole moment which has a magnitude q into 2a, already towards the positive y-axis. It's already towards the positive y-axis, already there. Okay, so when it is already there, so how much is the net now? Net is given as, you can say this one was 2 into QA already in y-axis, plus this yellow color vector which is already again 2 into QA, right? So the sum is actually 4 times of QA. So this is the net dipole moment. And can you guess the direction? Direction is the y-axis itself. So we write down it is j cap y-axis. So you are able to write down the vector form of net dipole moment. Okay, this is how we solve it, and this can be our final result, final answer, right? So this is the electric dipole moment ka net, right? Now let's see one more question. Fine, again you have a ring here. Find dipole moment in the given case. Means the dipole moment here, when you have a ring and that ring is having half of it with a positive charge, let it be plus q uniformly, and the other half with a negative charge. You can see like this. Upper semicircle is a positive charge, lower semicircle is a negative charge. First of all, how can we convince that yes, this is a dipole? How can it be convinced? So what do? We just take, say for example, I am taking a small element anywhere, a small element of positive charge here, small element here. What can be the charge of this? Let it be small charge dq, but it is positive dq. But as you can see, there is always at the opposite end of it, just at the opposite end, it can be said that there exists a similar charge minus dq on the opposite side, and the distance between them is obviously the diameter. So if I ask, is this a dipole or not? I mean these two, yes. So negative q, say we can have from the negative q to positive q a dipole going from negative point to positive point. So likewise in every arrangement, you have for every negative charge corresponding positive on the other end. You have for every negative charge positive from the other end. From every negative you have positive on the other end. For every negative you have positive on the other end. So this arrangement is a dipole. But you can see there is a very complex number of dipoles. How many number it can be? Since they are not the point charges, so we can imagine infinite dipoles here. Infinite dipoles. So how do we deal with this? Either you have to go with a conventional method, or we can say with a method using the integration, by which we can have first of all a dipole moment for a very small charge. Then we will say for that dipole moment we will integrate this element of charge from, say if this is vertical, from minus 90 degrees to plus 90 degrees. This is how we can do it. This is one of the ways. But I would suggest that if you remember that in one of the chapters by the name of center of mass, if there is some mass distributed over half ring, we choose a point where we assume that the whole mass of this body is assumed to be concentrated, and that whole mass where it is concentrated, that point used to be called as a center of mass. And for this body, the center of mass lies from this axis, which is actually the diametrical axis. From this diametrical axis, the center of mass lies at the height which is 2r upon pi. R used to be the radius of this half ring. Okay, so if this is a half ring, center of mass used to lie at 2r by pi distance from its center in the upward direction. Upward means here perpendicular to this diametrical direction, right? So now here also, if there is a ring, half of it is positive, another half is negative. So we can imagine the positive half is having the center of charge. There is the center of mass. Here I will say positive is having a center of charge. It means the whole positive charge is assumed to be concentrated somewhere here. At what distance? 2r by pi in the upward direction. In the same manner, we can imagine that the negative part is also having charge of minus q, and it's also at a distance of 2r by pi from this diametrical axis. So technically you have now a diametrical axis and this is having two charges. One is plus q and there is minus q. Okay. Now that plus q is at a distance of 2r by pi from this dotted baseline, we can say this diametrical axis, and another is also at 2r by pi. So technically we can say this positive q and negative q are having a distance between them, and the distance is 2r by pi, 2r by pi, double of it, it becomes 4r upon pi. Now where is the dipole moment? You can say, so dipole moment goes from positive to, sorry, negative to positive this way. So dipole moment goes in y-axis, so we can write down here what is the net dipole moment, one of the charge into distance between them. So one of the charge is q, distance is 4r upon pi. This is the net dipole moment, and where is it heading? The net dipole moment is towards the positive y-axis. We write down j cap. So this is the vector form of it. Magnitude is q into 4r by pi and the direction is positive y-axis. So this is our final result. I hope it's clear here, but I am telling you here, this is just a ways of we can say in a simple technique we are using. Otherwise the proper method of it is to go with an integration and do it for the point charges, but we had used a concept of center of charge here. Actually the center of charge is used only here when we are about to calculate the dipole moment only, right? So let's see one more thing. Okay, now it's given there are a charge A and charge B, and magnitude of each charge is given. As you can see, they are opposite. Plus 2.5 10 power minus 7 minus 2.5 10 power minus 7 coulombs. They are kept at two different locations A and B, where the x coordinates are 0, y coordinates are 0, and you can see only there is the z coordinate. Z coordinate is changing. That means A charge, means positive charge, is kept at the negative side of the z axis. So if we choose this to be the z axis, it is the positive z, negative z. So where is this positive charge? Positive charge is given at minus 15 centimeters, positive q, and we have one more negative charge here. So it is given at again 15 centimeters. So we can say fine, this is 15 centimeters from the origin in backward direction, this is also 15 centimeters from the origin in the forward direction. So where is the dipole moment and how much it is? Obviously dipole moment exists from negative to positive. Clear? Negative to positive. So in this example, so the net dipole moment is not in positive x-axis, sorry, positive z-axis. Net dipole moment goes in the negative z-axis. That's our answers which are expected. They are expected to be in the negative z. So this is minus k cap, so this may be the option. This is plus k cap, this is never the option. Minus k cap, this may be the option. Plus k cap, this is never the option. Okay, now let's see in these two what is the answer. So we find out how much is the magnitude of net dipole moment, one of the charge into distance between them. So what is the charge? It's given as 2.5 10 power of minus 7 coulombs, and the distance is 15, and 15 becomes 30 centimeters. So you will write down 30 into 10 power of minus 2 in meters. So our SI unit is coulomb into meter. As you can check from the result, from the options, it is coulomb meter. We solve it, we proceed with that. Okay, so I guess it will be equal to, it is 7.5, 2.5 into 3, 7.5 into 10 power of minus 8 coulomb meter. So this is our result, and we choose the correct option here to be option number C. Option number C here, 7.5 10 power of minus 8 coulomb meter. Okay, that fine. Now let's do one more problem. Again we can see how much is the dipole moment. I hope it's very easy here to do it. First dipole is minus to plus, second is minus to plus. Where this plus 2q can be imagined like it's the sum of two positive charges plus q and plus q. Okay, so how much is the magnitude? So magnitude of each dipole is given as q into distance. Distance here is a. Here also it is q into distance is a. So you have two vectors perpendicular to each other. So one is left, one is downwards. negative x-axis, negative y-axis. So we have result of these two, one of the value into root 2, one of the value of these, because they are equal, multiplied by root 2. This is by the vector results. Okay, so our answer is qa root 2. So root times of a into q, that's it. Root times of root 2 times of a into q. Okay, now we have one discussion on what is the electric field due to this dipole. Okay, fine, we have a dipole, it has the charges, equal and opposite charges, but what is the electric field due to this dipole at different locations? And here the discussion which we will be having, that is for short dipoles. I will tell you what is the short dipole. Let's say for example, for a particular dipole, we choose first of all axes, we choose the axis. We say that line which is passing through the two charges, as you can see this one, this line is called as axial line. Axial line. Okay, now there can be also one more line, the line which is perpendicular bisector, I mean which is at 90 degrees also, but also perpendicular to it. This line is called as equatorial axis. Equatorial axis. Now this is the axial line, or we can say equatorial line also, equatorial line. Axial and equatorial. First case is, what is the electric field somewhere at an axial point, means on this axis. Okay, so on this axis, if I choose to have a point, suppose I am having a point P at this, so what is the electric field at point P? Electric field at point P, obviously electric field can be only because of the positive as well as negative charge. So if this is positive Q, at this point P, electric field will be away from it, so we have the electric field due to positive away, and at this, because of this one, electric field is towards it, so we write down towards it, so that the net electric field at anywhere can be given as, net electric field can be given as electric field due to positive side, positive charge, minus electric field due to negative. And which one will be having more? See, this magnitude will be more, so it is towards right, it is towards right, that's why I write down EQ. Why? Because this point is closer to the positive charge. When it is closer to the positive charge, that means that direction is going to dominate, so that's why we can say this EQ towards the right, that is more. So and the net dipole here, net electric field is towards right only. So how much is that value? So we can calculate it using a formula of a point charge. Again I am telling you, distance is r. Distance r means this distance is actually from the central of the dipole, distance is r, center of dipole. Actually if this is the center of dipole, as I said, it is double of a, means this minus q is at a distance a, plus q is at a distance a from the center. Every distances I am taking from the center. So you can use for this one formula k into, I mean Coulomb's constant into one of the charge, I mean q charge positive, upon distance ka square. So what is the distance from the positive charge? It is r minus a ka whole square, r minus a whole square. Then you will subtract it, because we are just taking the magnitudes only, direction we know it is towards right, and subtract the electric field due to this one. How much is this? K into charge upon, now what is the distance of this point from this negative q? Obviously it is r, and then add plus a, r plus a whole square. This is the electric field. Now when we calculate this, we do the calculations and all. I am just skipping those calculations, you can try it by yourself. We get some result, and even in that result, if I take this distance, which is a, actually a, or this 2a, it to be less than r, I mean the distance of this point from a dipole, from its center of dipole, this r distance, it is much greater than the length between the charges, or the dipole length. It is much greater than the dipole length. That type of dipole is called as short dipole. Short dipole. You can imagine a short dipole by just having two charges. Let this be the dipole, plus q minus q. Okay, this is minus q plus q, and you know the distance you are taking at much larger distance here. I mean, the dipole is so short that their length is very, very small as compared to the length where you are finding the electric field. The point where you are finding the electric field on an axial line, it's much larger distance, and the length of the dipole is very short. And for that dipole, when we do the calculations, I mean, we proceed with this derivation, or we proceed with these numbers, and when we apply it, we get the electric field at this particular point P, which is on the axial line here. We get it in the magnitude of it is 2 times of Coulomb's constant times of dipole moment 2 kp upon r cube. We get it as 2 kp upon r cube. That's it. So when we proceed, we get this as a result. So this is the electric field at an axial line. Electric field at an axial line. So we have the two things to know here. First of all, what is the magnitude of that electric field? Magnitude is 2 kp by r cube. Okay, so it means that the variation of this particular electric field with the distance is not inverse square. No, it is inverse cube, right? Which is just as contrary when we have the point charge. Okay, when we have the point charge, if you know the results for the point charge, for the line charge, and also for the sheet charge. If I have some distance r from it, and here r from it, and here r from it, so what are the electric fields? How are the electric fields varying? So in all these results, electric field varies as, in the first case, inversely proportional to the square of the distance if it is a point charge, and here inversely proportional to distance only, and here it does not depend on distance because it was sigma by 2 epsilon naught, if you remember the results. So that's it. Okay, now here we can have this as 1 by r square, 1 by r, and it does not depend on r. But you can see a uniqueness here in the result of electric dipoles. The electric field varies inverse to the cube of the distance. That means if I double the distance, right, electric field will get reduced. How many times? Double means 2. 2 ka cube, 2 into 2 into 2. It will reduce by 8 times. Okay, this is the significance of this cube, right? Now the second part, second thing about to know is direction. Where is this electric dipole? Net electric field, where is that? You can see the dipole moment was from minus to plus. So it is towards right here, we can say positive x-axis, and when we reach here, so the electric dipole will again be from minus to plus. So it will be in the same direction because I know that the positive charge is dominating in the electric field. So the direction will be assigned as per the positive. It is towards right. This is also towards right. So we say electric field and dipole moment are in same direction. But it is true only for the electric field at an axial line. We are discussing the axial point. Electric field at an axial line anywhere is, and dipole moment, they are in same direction. They are in same direction. It means if I have a dipole moment upwards, and I want to know what is the electric field anywhere on this line. So if you go on the positive side of it or the below line of it, in both the cases electric field is up. Here also it is up. So it means if you have a dipole somewhere and you want to know its electric field, where is the electric field due to this dipole? In the line of it, I mean axial line, it is always there where the dipole is. If dipole is up, electric field behind it is also up, electric field in front of it is also up. So this is the direction of electric field. Okay, I hope it is clear. Now we will go and see what is the next discussion, that is electric field at equatorial point. Now what is this equatorial point? As I said, there is always one line which passes through the axis, we call it axial line, but there is also another line which passes through the midpoint as well as perpendicular. This one is called as equatorial line. And for that equatorial line, if I choose to have a point again which is at much distance as compared to this, so again I am telling you, let's take a short dipole. Means this a distance, or we can say the length between the dipoles, between the charges, it is less than r, much lesser than the distance of a point where you are finding the electric field. Now let's see. Again, electric field is the net electric field is the consequence of the individual electric fields. So here we can see the electric field due to the negative is towards the negative. So that's it. And electric field due to this positive is, you can see positive is away from it. So if we have that point which I have chosen there, okay, it has now two components or two electric fields, E positive here and E negative here. E positive, E negative. So it is the electric field due to the positive charge, it is the electric field due to the negative charge, and you can just imagine by the vector calculations where is the net, their resultant will be here. It means that if the dipole, you can see the vector sum of these two is obviously here, this side. So it means that if the dipole moment is here, you can see from minus to plus, negative to positive, here it is positive x-axis, and when we calculate the electric field net on a point at equatorial line, okay, so you can see it is opposite. So the first thing here we would like to write down is that the electric field on an equatorial line and the net dipole moment are in opposite direction. And before that, if you see electric field and at axial point and dipole moment, they are in same direction. Here they are in opposite direction. And now again, if they are in opposite, what is the magnitude of this? Okay, how much is the magnitude? So if we go with the derivation, which I am skipping here, I will just tell you how to do it. So you can say the electric field of this one, see if this is distance r, this is a, so you can write down how much is this distance from the charge and this point. If I name it as d, it will be root of r square plus a square. And again by the symmetry it is also d. So the positive part of this electric field can be written as k into charge upon distance ka square. So that means it will be written as this d square ke badle root of r square plus a square ka whole square, it is r square plus a square. Now here also it is the same magnitude, kq upon r square plus a square, right? So these two are the vectors, and if you want to know the resultant between them, so you must be knowing what is the angle with which they are inclined. Okay, so for that angle you just need the cos of that angle, and cos of this complete angle will be just equal to the cos of, in magnitude it will be cos of this angle. Fine. So if the half of the angle on this side is theta, another half is also theta. Okay, so when you proceed with this, you can say that you can find out that electric field at this point is kp by r cube. Now what is uniqueness about this result and the result before it? The result before it was telling us that electric field at an axial point is 2 kp by r cube. Now here on the equatorial point it is only kp by r cube, which means that the electric field here in magnitude, if it is at the same distance, if we keep the distance same, so it is just the half of what we get previously, and also it is the inverse to the cube of it. So variation with r is same, inverse to the r cube, but the one thing is, if we choose to have 2 points, if we have this electric dipole, okay, and from that dipole I am saying let's say the distance of 10 meters from here and 10 meters from here, 10 meters from here and 10 meters from here. If the electric field on their axial line, if this is equal to 100 Newton per coulomb, what is the electric field at the same distance of 10 meters somewhere here? So obviously it is the half of it, it will be 50 Newton per coulomb. Correct? And also one more thing, if the dipole has a direction, this one, positive x-axis, so you should be knowing electric field here is a positive and electric field here is negative. Understand? So we can say for the same distance, if we have the same distances along both the axes, correct? So electric field intensity at equatorial or electric field intensity at axial line upon electric field intensity at equatorial, which one will be more? Obviously this is more, and the ratio of this is 2:1. You can see because this one was 2 kp by r cube, it's only 1 times kp by r cube, so the ratio is 2:1. This is how we deal with it. Is that clear? So now we have the two discussions, electric field due to the axial line, electric field due to the equatorial line. I hope it's clear. Now let's go and see if I tell you this problem, right? In an equatorial position, what is the angle between net electric field and dipole moment? Okay. So we are asked actually if there is a dipole and on its sorry, not axial, equatorial position, if there exists a electric field, what is the direction between this electric field and dipole moment? As we did previously, if it is dipole minus q plus q, if the dipole moment is towards right, electric field is towards left on an equatorial. So if some one vector is right, one vector is left, so what is the angle between them? Angle between them is 180 degree. This is the result. Remember, we will not use here angle is 90 degree. This is not a correct thing. It's not 90. Sir, why not? Because 90 is not the angle between the dipole and the field. 90 is angle between the dipole direction and the axis. But it is asking us net electric field and the dipole. So it is asking between field and the dipole, not the field and the equatorial axis. If it asks what is the angle between the field and the equatorial axis, then the answer was 90. But if it is asking the dipole and the electric field, dipole is towards right, electric field will be just opposite of it on an equatorial line. So that's it. So this is how we complete it. Now let's see one. Okay, let's do this one. There are two dipoles, short dipoles given. We have the distance r and r. For the first one, if you see, if I choose this one as first, if we see this one is the first, so at this point P lies at an axial line. So we can have electric field due to this one going towards right. Okay, now choose this one as the second dipole. I am denoting it with pink color. So this is the dipole. Now this line is the equatorial line for the second dipole. So for this second dipole, where is it? Where is it? So it will be opposite to it. So I am using opposite. What is the value? What is the magnitude? So the first one will be having a magnitude, first one, which is denoted by the red color, since it is on the axial line of this and the distance is r, we write down 2kp by r cube. And where is the second one magnitude? So since it is on the equatorial line at a distance r, we write down only 1 times kp by r cube. So how much is the net electric field at a point? Since electric field is a vector, one is forward, one is backwards, so it is given by subtraction of them, 2kp by r cube minus kp by r cube. And now your answer is kp by r cube. This is the result. I hope it is clear. And the discussion of electric dipole, I would like to end it here. The other